The next section we're going to look at is double angle formulae. These are very similar to what we did before, but they just use a different set of formulas. So we're going to look at some examples here. So the first one says, from the diagram find the value of the cos of 2a without using a calculator. So this 2a here, that's our double angle. So we don't want to use a calculator, so we have to use a different method. So first off, we can draw the triangle. So we know that we have an angle A, and we can then set the other sides. So from our diagram, we know that the base is twice root 2, the vertical is 1, and we can then find h. So we use Pythagoras' theorem to find h. So we get 1 squared plus twice root 2 squared, which gives us plus 9. The square root then of 9 is plus or minus 3, so h must be 3. So we then can assign that the sine, which is opposite over hypotenuse, that's 1 over 3, and the cosine is adjacent over hypotenuse, so that's twice root 2 over 3. So we now have our two expressions that we'll need. So when we go look to the tables on page 14, we'll get this expression that the cos of 2a is equal to cos squared a minus sine squared a. So they tell us not to use our calculators, so having these expressions now lets us do it basically in our head. So we square the top, so that's 2 squared 4 by root 2 squared, which is 2, so 4 by 2, which is 8, over, that should be a 9 there. So again, square the top, square the bottom, that gives us 9, so 8 over 9 minus 1 over 9, so the cos of 2a is 7 over 9, all done without using a calculator. On our next example, we have this one here. So, in a second. Yes. So prove that the cos of 3a is equal to 4 by the cos cubed a minus 3 times cos squared. If you're very stuck on these, they're kind of standard results, so you will find them online, but it's nice to be able to work out through them. So the first thing we got to do is we don't have any triple angular formula, so we got to break it down. So we use back into the sum formulas. So the cos of 3a, we can write that as the cos of 2a plus a. So then if we want to express this as the cos of two different angles, we can have the cos of a plus b from page 14 of our tables. That gives us cos a cos b minus sin a sin b. So in this case, a is replaced with 2a and b is replaced with a. So we sub those in, so the cos of 2a cos of a minus the sine of 2a times sine of a. So we get this new expression here, which is on page 313 of your textbook. This expression isn't in the table, so it's one that's kind of useful to remember. You can derive it, but it's easier to remember it. So you can have a new way to write this, the cosine of 2a, and that way is twice cos squared a minus 1. There's another version for this, but this is a more useful one to go with because this brings us in our cosine rather than a sine, and in the end we want to have all of these things as cosines with the power cubed, so we try and bring in some higher powers, which we'll be able to work that out. As you can see here, we can then just slot that in. So we take this line and rewrite it, so the cos of 2a plus a is equal to a new expression times the cosine of a minus the sine of 2a sine a. So just left that alone for the moment. Again, we can multiply this one out here, so we get the cos of a multiplied by the first bit, which gives us twice cos cubed a, and then the cos of a times minus 1, which gives me minus the cos of a. So I have already got my cos cubed term in, so I'm progressing towards the finish. I then can use this other expression, which is on page 14 of your tables, that's your double angle formula, so I can replace this sine of 2a with twice sine a cos a. So then when I go back to my formula, I have my left hand side as before, twice cos cubed a minus cos of a, then minus this subbed in twice sine a cos a, and then my sine a that's left over. So I then multiply this in, so I get twice sine squared a, so sine a by sine a gives you sine squared a by the cos of a. Now it's just a matter of tidying it up to get it into the form that they want. So we have sine squared a. Again, another expression for that because we don't want any sines in our answer. They've got to be all cosines. So sine squared a is equal to half times 1 minus cos 2a. So we sub that bit in there. I've took off this right side bit into brackets. Just that minus kind of caused me a couple of problems and I went head first into it. So you just multiply all of this out. So we get twice 1 by twice cos squared a. Then we multiply the cos in by those two terms, and we get this line at the bottom of twice cos cubed a minus cos a minus twice cos a plus twice cos cubed a. So that, when I add the like terms, I get the expression they want. Cos 3a is equal to 4 cos cubed a minus 3 cos a, as required, as a nice way to finish off the question. Then the final one I've done out here is there are two acute angles a and b, and they are such that the tan of a is 4 over 3 So that's the first angle is 4 over 3, and then the tan of A plus B equals minus 1. They tell us without evaluating A or B, which is kind of like without using a calculator, we have to show that the tan of B equals 7 and then evaluate twice the sine of 2B. So because I'm given these expressions in tans, the first thing I look up is what is the tan of A plus B. So on page 14 I get this expression here. So the tan of A plus B is tan A plus tan B over 1 minus tan A tan B. I know in this case when the question of the tan of A plus B is minus 1, so I sub that in, and I know the tan of A is 4 over 3, so I pop that in here and here to get this expression. Again, after that it's just a matter of tidying up with algebra, so multiply both sides by the denominator to get minus 1 plus 4 over 3 tan B, and that's equal to the top line 4 over 3 plus tan B. Rearrange it and I get the third tan B equals 7 over 3, and then tan B is 7. For the second part I kind of did a little bit more work than I needed to, so it's not that essential, but again it might be somewhat useful. So I was told that I had two angles A and B. I can make those both into right angle triangles, and then if I put one of them on top of the other, that will give me the combined A plus B into one diagram. It's important you don't think that it's A and B up here. That wouldn't be the case. So they have to be separate triangles. We know that, then we were told earlier, that the tan of angle is 4 over 3. So that means opposite adjacent is 4 opposite and 3 adjacent. Again, you should know it by heart, but right angle triangles 3, 4, 5, so we can just pop 5 in there or go the longer way and use the Pythagorean theorem. We know here, and we were told it even if we couldn't find it out, that the tan of B is 7. So if we know that this adjacent side is 5, so we can figure that out from the attached triangle because they're two angles A plus B. So tan of B is 7. So the tan of B in general is opposite over adjacent. So I can swap this in. I call the opposite y and I call the adjacent 5. That has to be equal to 7. So that means y is 35. That lets me write B in all three forms. Again, I can find this out with Pythagorean theorem. So 5 squared plus 35 squared equals this squared, so get the square root and you get this figure here. So I can now get an expression for the sine of B, the cosine of B, and I already knew the tan of B, 35 over 5 or 7. So the sine of B is opposite of 35 over hypotenuse, which is this. I have the cos of B, which is adjacent, which I found to be 5 over the hypotenuse of this, and then opposite over adjacent, 35 over 5. So what I did first, so just go down this side and to the right hand side, was I just looked at the tables, and first off I'd see that I'm asked for the sine of 2a. So the sine of 2a I saw is this. So because I needed this, that work was kind of important. So I can see here the sine of, and again the sine of 2a equals twice sine a cos a, but the angle I'm dealing with is b. So just rewrite that expression using a b, and then I have the sine of 2b equals twice from the formula. The sine of b is this, so slot that in here. The cos of b is this, so I slot this in here. Then I can kind of cancel it down. 5 goes into both on each of them, multiply across, and I get down the answer of 7 out of 25. Again, I could have simplified those up there, but I didn't really think to, and you could throw that in the calculator. Nobody could argue you didn't do it in your head. Then the easier way to do it, which I should have done in the first place, was I can just use this expression. The sine of 2a equals twice tan of a over 1 plus tan squared a. I found out in this expression what the tan of the angle is, and again, a is just in the formulas I'm dealing with b, so it's really the sine of 2b equals twice tan b over 1 plus tan squared b. I know that's 7, so I didn't really need any of this work down here. I could have just finished it out quickly like this. So the tan of the angle was 7. The tan of the angle squared is 7 squared, so I get twice 7, 14 over 50, 7 squared plus 1, which gives me 7 out of 25. So the same answer whichever way you go. So we can see the similar kind of rules as before. Some of them are trickier than others. This one, you just have to use the formula straight off. You could have used Pythagorean theorems and diagrams and things like that, or you could have just gone straight to this one. The hardest one was probably question 7 here. So again, you got a good bit of substitution to do there. So you got to use a lot of the formulas from the tables, and one of them that is an even. And then the first question was again a little bit like what we did yesterday. You can create right angle triangles, use Pythagorean theorems, you get your expressions, and you can work these things out without calculators.